Let's continue learning about Pascal's triangle. We want to really understand why this triangle is so beautiful. Uh, this was the triangle that we talked about in the previous video. 1 1 1, 1 2 1, 1 3, 3 1, 1 4, 6 4 1, and so on. And we noticed a very secret but important relation of these numbers with binomial coefficients. This is 0 choose 0, this is 1 choose 0, 1 choose 1, this is 2 choose 0, 2 choose 1, and 2 choose 2, and so on. If you do not know why this is true, you should watch the previous video. There is a very beautiful way of thinking about this, and you should definitely watch the previous video to understand why this is the case. Okay? Now, the problem that we want to address is the pattern of the Pascal's triangle. Notice that these two numbers, they add up to give you the number in the middle of the next line. This is the general pattern of the Pascal's triangle, right? Even if you did not know anything about 1 choose 0, 1 choose 1, all of these things, you could actually write down the next line of the Pascal's triangle. How? Well, you would just naively start with 1, add these two things to get the next line, and keep on doing the same thing to get the next line. And you would get precisely the numbers that you would actually get thinking about the choices. Why is this happening? Why is this happening? Because this is, after all, 4 choose 0, 4 choose 1, 4 choose 2, and so on. So in some mysterious manner, if you join or if you add these two 3's, you get 6. But also, if you add 3 choose 1 and 3 choose 2, you get 4 choose 2. And this is the thing that we wanted to discuss today. This is sometimes known as Pascal's identity. Pascal's identity, or the identity of the Pascal's triangle. We want to learn this. We want to understand why this is happening. And we want to do this using something called combinatorial argument. So maybe you know a formula for n choose r. Maybe you know a formula for n choose r. Some of you may already know this. I don't want to use this formula. I want to instead use just an argument, just reasoning, to find out this fundamental fact about Pascal's triangle. That is, if you add these top two objects or numbers, you will always get the number in the middle of the next line. So let me generalize this. Suppose you are in the nth line. Nth line. That is, you start with the 0th line, which is 0 choose 0, which is basically the number of ways of choosing 0 things from 0 things. I told you this is the do nothing case. There is only one way of doing nothing, hence we write this is equal to 1. This is a naive way of thinking about this. 0 choose 0 is basically you choose 0 objects from 0 objects. So basically you do nothing, but that is doing something. Doing nothing is doing something, and that there is only one way of doing that. Just do nothing. That's one way. So we write that number as 1. So nth line, we have n choose r, and then we have n choose r plus 1, and then we go to the n plus 1th line, and the object in the middle here, right here, is n plus 1 choose r plus 1, this one. So this is n plus 1 choose r plus 1. So that's what we want to show. We want to show that n choose r plus n choose r plus 1 gives you n plus 1 choose r plus 1. And we want to do this using arguments, using something called combinatorial argument. So n choose r plus n choose r plus 1 is equal to n plus 1 choose r plus 1. This is our goal. This is what we want to show using arguments. But just to take a step back, what is the meaning of n choose r? This is the number of ways of selecting two things, or r things in this case, r things from n things. Number of ways of selecting r things from n things. And I gave you an example that suppose if n is equal to 3, so we have 3 objects, 1, 2, 3, and if r is equal to 2, so we want to select 2 of them. Then explicitly we have 3 ways of doing that. So 3 choose 2 is equal to 3. Why? Because there are 3 ways of doing that, of choosing 2 things out of 3. Why? Because you could either, so case 1 or choice 1 is you could either choose the first 2, or case 2 you could choose the first and the last one, or case 3 you could choose the second and the last one. So there are only 3 ways of selecting 2 objects from 3 objects. So that's why 3 choose 2 is 3. I'm not going into the formula at all. I just want to keep this at the very naive level. That is, suppose I don't know any formula for n choose r. How do I approach this problem given that I do not know any formula for n choose r? Just using arguments. So coming back, we want to prove that n choose r plus n choose r plus 1 is equal to n plus 1 choose r plus 1. Instead of choose, I am writing C. Okay. Alright. So here is the argument. Suppose we have the n plus, so let's look at the right hand side. The n plus 1 objects. The n plus 1 objects are A1, A2, A, n plus 1. There are n plus 1 objects, so I give them names. They're all distinct, by the way. Distinct n plus 1 objects. Now I want to select r plus 1 of them. So goal, select r plus 1 of them. Now we have two cases. Case 1, A1, if you look at A1, A1 is in the selection. So when you select R plus 1 objects, A1 might be in your selection. If that happens, then you have to select remaining n objects, remaining R objects, because you have already selected one, which is A1. You have to select remaining R objects, select R objects from n objects, right? From n objects. Because ultimately you have to select R plus 1 of them. One of them is already selected, which is the case 1, where A1 is already there in the selection. So you have to select the remaining R objects, and you can do it from the remaining n objects. So the number of ways of doing that is n choose R. Okay, the case 2 is this. A1 is not in the selection. A1 is not in the selection. That means you have to select R plus 1 objects now, because ultimately you want to select R plus 1 objects. A1 is not in the selection, so this R plus 1 objects must be selected from these remaining n objects. Because A1 is not there, so you only have n choices, and you have to select R plus 1 out of them. That means that's n choose R plus 1. Notice that only these two things can happen, because either A1 is in the selection or it is not in the selection. It is either in the selection or not in the selection. Both of these two cases cannot happen together, and they together create all the cases, because whatever choice you make, A1 is either there or it's not there. Both cannot happen together, and neither is happening. That cannot happen. Either A1 will be in the selection, or it might not be, or it is not in the selection. Either it is there or it is not there. I'm stressing this fact over and over again. Think about it. So these two cases, the two cases that we have here, they together create all the cases that we want. Hence we have the required identity. So finally we have n plus 1 choose R plus 1, which is all the cases, all ways of choosing R plus 1 objects from n plus 1 objects. This is equal to case 1 plus case 2. Case 1 is n choose R, and case 2 is n choose R plus 1. So do you see what we just did? We created the formula that makes Pascal's triangle. Okay, keep on thinking about this and do some more mathematics, and I'll see you next time. All right, bye.